Welcome back. We now know how to write equilibrium expressions. We know that they're constant no matter what we do, as long as we've reached equilibrium, right? So what we're going to find out now is what happens if we do some calculations and our concentrations don't equal up to K. We do the calculations, we plug everything in, and we don't get the right K value. So here's an example. We've got making ammonia from nitrogen and hydrogen gas. We know that the K value of that is 0.06 at 500 degrees Celsius. And we're going to put this following concentrations into our chamber, and we're going to try to figure out what's going to happen. So if we plug this in, if we're at equilibrium, we know for 100% certain that we are going to get 0.060 if we plug all these things in and do the math. So let's go ahead and write our K expression. We know that K is going to be, these are all concentrations, so it's a K, not a Kp. NH3 squared divided by N2 to the first divided by H2 cubed. That's our K expression. Now let's go ahead and plug these guys in here and say, look what happens. So our NH3 we're going to get from here is 1 times 10, oops, let me do my sig figs, right? 1.0 times 10 to the minus third. We're going to square that. And then our N2 is 1.0 times 10 to the minus fifth. And then our H2 is 2.0 times 10 to the minus third. And we're going to go ahead and cube that. If you do that, you get 1.3 times 10 to the seventh. And you're like, well, shouldn't I have gotten 0.06? And the answer is, you should have gotten 0.06 if you were at equilibrium. But the fact that we didn't get that this is not equal to 0.060, means we are not at equilibrium. That's what it means. So we now know that this reaction actually will react in order to come to equilibrium because we got a value that was not equal to our K value. Even more so, we can actually predict which way the reaction is going to go. We found that this value was much, much larger than our actual K value. But now we're getting a little confused because I've got a K over here, and I've got a K over here. And am I talking about that K value or this K value? And it gets a little confusing. So what we do is we use K when we know we are at equilibrium. So we use K when we could actually write a subscript on each of these guys that says EQ, EQ, EQ. But if we don't know we're at equilibrium, we use the letter Q. The form is exactly the same, NH3 squared over N2 times H2 cubed. So you'll notice K and Q have the exact same form, but K we only use when we know we're at equilibrium. Q we use when we don't know. If we're at equilibrium. Okay, so Q is more general. So what we actually calculated here is that Q is equal to 1.3 times 10 to the seventh, because we didn't know, nobody told us that we were at equilibrium. They didn't say these were equilibrium values. They said they were initial values. So this Q is now much, much greater than our K. So I can write it this way, that Q is much, much greater than K. What does that mean? Well, we know that as it reacts, it's going to get closer and closer to K. So if we're already starting off big, right? If we've got a big number, you know, a million or 1,000 over 1, and we want to get that number down to 10 over 1, what do we have to do? Well, over time, we have to make this smaller. Right? We have to make that numerator smaller, otherwise we won't get down to 10. Now, in stoichiometry, you can't just make the numerator smaller. You're also going to make this guy larger at the same time. Why? Because in order to make the numerator smaller, you're going to take products and turn them into reactants. But as soon as you turn them into reactants, you've made the denominator smaller, which is your reactants. If that was a little confusing, don't worry about it. What does this mean? Q is greater than K. Since Q at equilibrium has to be equal to K, right? Because that's just the definition of Q. It's got the same form. So at equilibrium, it's equal to K. We're going to edge towards a situation where Q is equal to K as time progresses. Since Q needs to decrease, what does that mean? It means that the concentration of our products must go down, and the concentration of our reactants must go up, which means our products are going to be forming reactants preferentially. Not entirely, right? Dynamic equilibrium, there's always reactants forming products and products forming reactants, even as it's running. But in the long run, what's going to happen is our products are going to go down, our reactants are going to go up, and we're going to say this reaction shifts left, right? Because reactants are always written on the left, products are always written on the right. So as we increase reactants and decrease products, we call that the reaction shifting or moving to the left. You can also say the reaction is shifting towards reactants or shifting towards products, but for whatever reason, people generally use left and right when they talk about this. If Q was much less than K, if Q was way too small, we'd have to increase that numerator, which is our products, and decrease the denominator, which is our reactants, and we say the reaction shifts to the right. So if Q is greater than K, reaction shifts left. If Q is less than K, the reaction shifts right. And let me actually copy that one over here, just to distinguish something for you, is that it doesn't have to be much, much greater than. It's just if it's greater than. Okay, so even if Q is just a little bit greater than K, the reaction will shift left a little bit. If Q is just a little bit less than K, the reaction will shift right a little bit. But obviously, larger differences mean larger shifts. If Q is equal to K, right, you didn't know if you were at equilibrium, but you found that it equal to K, then the reaction is at equilibrium. And so you've actually found, by doing the calculation, that your reaction is at equilibrium. So we're actually going to use this Q value a lot when we don't know what's happening. When we have come across a system and we say, oh, we've already got all this stuff in here, what's going to happen? We're going to calculate Q and figure out, is the reaction shifting left? Is the reaction shifting right? Or is the reaction already at equilibrium? Because that will help us determine how to best proceed forward. So here we go. We've got the reaction of nitrogen and hydrogen forming ammonia. K is 0.60. We've got these different starting concentrations than in the previous slide. And I want to know what's going to happen. Is the reaction going to shift to the left, shift to the right? It's at equilibrium? Or we can't tell because we need some more information. So go for that one and then see what you get. What'd you come up with? All right. Well, hopefully what you did is say, hey, I've got these concentrations. I don't know if my reaction is at equilibrium. Let me calculate Q. It has the same form as K. I'm not going to write it again. As we already wrote it on the last slide, I'm just going to plug in my numbers. I've got ammonia 2.00 times 10 to the minus fourth. I'm going to square that one. My N2 is 1.5 times 10 to the minus fifth. And my H2 is 3.54 times 10 to the minus first, or 0.354. And I'm going to cube that one. If I plug all of that into my calculator, I get 0.0601. And so my K was 0.060. Are those numbers equal? I mean, mathematically, they're not, right? 0.060 is not the same mathematically as 0.0601. And so you might say, hey, Q is greater than K, so the reaction's going to shift to the left. And, you know, it wouldn't be unreasonable to say that. However, what do we also have to look at? We also have to look at, do we really know that that's a 1? Well, how do we know? We look at sig figs. 2 sig figs means we only have 2 sig figs in our answer. And our answer for Q is actually going to be 0.060. So within our significant figures, it looks like it's at equilibrium. But if you don't include significant figures, it looks like it might shift to the left. So which is it? It can't be both. It can't both be at equilibrium and shifting to the left. And the answer is, we don't know. To within the precision that we know it, this reaction is at equilibrium. But precision is not perfect, right? We don't know perfectly this reaction is at equilibrium. So it could be that it's going to shift slightly to the left. It's quite possible. But given our significant figures, we're going to call this reaction at equilibrium. But if you came up with left because you went for that extra digit, you totally got the concept right. But you do have to keep track of your significant figures and say, do I know that that's going to happen? Or within my significant figures, is this reaction at equilibrium? All right. So let's go ahead and do that one. Is we're going to call that correct answer. The reaction is at equilibrium within our significant figures. So what can we do with this? We're going to use the fact that the equilibrium constant is constant in order to calculate things, right? Oftentimes we start off with stuff and we want to know, well, how much did we make? We did a lot of that kind of stoichiometry in first semester general chem, right? Oh, I've got A plus B, 5 grams of this, and you did that stoichiometry. But now that we've got equilibrium, that's a little more complicated because I'm not going to make all of my product. I'm going to still have some reactant left, and how much do I have left? That's what we're going to kind of take on in this next section. I just want to show you this table. And what this table shows is for a reaction of carbon monoxide with hydrogen to make methane and water. There's a bunch of different starting conditions. Here I've got 0.1 molar CO2, 0.3 molar H2, so all reactants. Here I've got, I'm sorry, that should be a CO, not a CO2. Here I've got different concentrations of them. And here I've got no reactants to start, and I've got all products. I let those run to equilibrium. I find my equilibrium concentrations. I calculate K, and darn it, that thing is pretty well constant. Okay, it's got a little bit of variation in that last digit there, but that's kind of normal. We expect that from experimental variations. But it really doesn't matter. We can start with all reactants, all products, let it come to equilibrium, and it's fine. Start with reactants and products, let it come to equilibrium, and we'll always get that same K value. And that's going to be what's very, very useful to us. So we're going to do a few applications of this. Our first one is just to find a missing value. And it turns out N2O4, dinitrogen tetroxide, was used by the Apollo missions, the moon landings, as a rocket fuel, because if you heat it, not only do you go from a liquid to a gas, getting that expansion and kind of being able to kind of use it as a propellant, but every single N2O4 falls apart into 2 NO2s, according to this balanced reaction right here. So you actually get twice as much propellant, right? Twice as much gas for every 1 molecule of propellant. So people use that as a propellant because it also stores fairly well. So gaseous N2O4 is placed into a flask. Equilibrium constant there, Kp is 0.133. The partial pressure of N2O4 was measured, and I'm going to put in the words here, at equilibrium, to be 2.71 atmospheres. What's the partial pressure of NO2 at equilibrium? So you put it into a flask, you let it sit there long enough, and right, how long is long enough? Well, that's the domain of kinetics. We're just saying we're going to take long enough, but we're not going to say how long that's going to take. So what do? Well, when you're getting equilibrium problems, the first thing you always want to write down is your K value. Now, all these things are in pressures, and I've got a Kp here, so I'm going to write down that. And it's just going to be the partial pressure of NO2 squared over the partial pressure of N2O4 to the first. And let's figure out what do we know and what don't we know. We know that Kp is 0.133. We also know that at equilibrium, right? These are all equilibrium things. As soon as you write a K expression, they're all at equilibrium. If you don't want equilibrium, you write a Q expression. So we know that at equilibrium, the partial pressure of N2O4 is measured to be 2.71 atmospheres. So we're going to do this. We're going to say, well, we still don't know that one, but we do know this one, 2.71 atmospheres. And I write that unit there just to remind myself, yeah, it's atmospheres. But remember, we generally divide by a reference concentration, and so I'm going to take that off. If it was given in torr, remember, you got to convert those torr into atmospheres in order to solve the problem. But look, I've got an equation with one unknown. I know how to solve that, right? I multiply both sides by 2.71. I take the square root, so the P partial pressure of NO2 is going to be the square root of 0.133 times 2.71. And if you do that math and plug it into your calculator, what you get is 0.600 atmospheres. And you'll notice, right, we had no units in this thing, and all of a sudden I put that atmospheres on there. That's because what we calculated in here, the pressure of NO2 is actually the pressure divided by the reference pressure, so we have the unit of 1 atmosphere that we get back. You don't have to busy yourself with the reasoning behind all of that if you don't want to. Just remember, when you're talking about a pressure and you're just reporting a pressure, you better have a unit on that. But when you're putting those numbers inside a K expression, you are welcome to leave the units off, and most people do. So 0.600 ATM. That's kind of the simplest one, is we're given a bunch of equilibrium information and there's just one piece missing. That's just kind of a plug and chug into our equilibrium expression. That doesn't happen very often. What happens more often is we have initial conditions, because those are easy to measure. Those are things that I actually put in. I say, oh, I put in this much of this into a 1 liter flask, therefore my concentration is 0.75 molar. So initial concentrations are very easy to do because we are in control of those. But then if we want to calculate equilibrium concentrations, how can we do that? And that's what we're going to do next. So we've got this reaction here that we had a few slides ago. Carbon monoxide and water goes to CO2 and H2. We've got a K value for it at 1,000 degrees Celsius. And we're going to start with 0.02 molar CO, right? That's one of our reactants, and 0.02 molar H2O, another one of our reactants. And what we want to know is, what is the equilibrium concentration of all species, right? And species are not, animals and plants and things like that. They are just all the different chemicals. So what we want to know is the equilibrium concentration of CO, of water, of CO2, and of H2, everything that appears in that overall balanced chemical reaction. So how are we going to do that? That seems a little bit interesting, because we don't know how much it's going to make. But we did have that review in the last video of our stoichiometry. So let's see if we can use some of that video stoichiometry thoughts and figure out what's going on. So I'm going to write this reaction down here. I'm going to write CO plus H2O goes to CO2 plus H2. I'm going to think about it. What I want to do is I want to write down, what do I have as my initial conditions, right? In my initial conditions, what do I start with? And that is given to me as 0.0200 molar concentration of that and 0.0200 molar concentration of that. It's also useful to write down that I had none of these ones, because we're going to run across problems later on where we do have products. And so it's good to write down those zeros there and make sure we fill in everything. Now, as this reacts, you could totally do the stoichiometry on this one, right? 1 to 1 to 1 to 1. That's pretty easy. As I use up a CO, I make a CO2. As I use up a water, I make an H2. The stoichiometry is not hard on this one. But the difficulty is we have no idea how much CO2 we're making and H2 we're making. That's what we're trying to find out. But in math, when we don't know what we want, what do we call it? We call it X. So that's what I'm going to do here. Is I say, I know I'm going to be making some CO2, right? So this is a change that's happening, right? I'm going to be making some CO2. And the stoichiometry tells me that if I make 1 CO2, I'm also going to make 1 H2. And the stoichiometry tells me that if I make 1 CO2, I'm going to use an H2O. And the stoichiometry tells me if I make 1 CO2, I'm going to use up a CO. And so we have some stoichiometry that looks like that. Now, obviously, if we knew the numbers, we could just plug those in, but we don't, right? And so that's what changes. And we make some of this stuff and we use up some of our CO. Is that what we end up with? Do we end up with negative X of CO? No, we can't have that, right? We can't have a negative concentration of something. That's impossible. But what did we do? Well, we started with 0.02 molar and we used up some in order to make that stuff. And so what we're going to say is there's a third line here called equilibrium. And what I'm going to do is I'm going to say, hey, let's just add up these other 2 lines. I know that I started with this, my change was this, and so at equilibrium, I'm going to have the addition of those 2 lines, which is 0.0200 minus x, 0.0200 minus x, and x, and x. I don't know what those equilibrium concentrations are, but I can write a form for them. And let's see if that helps me. Let me go ahead now and write my K expression for this reaction. If you look up here, K is going to be the concentration of CO2 times the concentration of H2 divided by the concentration of CO times the concentration of H2O. And if you looked back up at the problem statement, that was going to be 0.58 at 1,000 degrees Celsius. How does that help us? We still don't know that value of x, so can we plug everything into k? We're not going to get 0.58, but remember, since we have 0.58, that's useful information that might get us x. What do we have in this line here? We have equilibrium concentrations of all of our stuff. Since we have equilibrium concentrations of all of our stuff, we can actually plug those into our equilibrium expression and get the following. X, right? Because CO2 and H2, if you look back at our table, right, that's those last two columns. CO2 and H2 were X. These were 0.0200 minus X and 0.0200 minus X. And that was equal to 0.58. Well, hey, look, I've got an expression. It's just got X in it and a bunch of other numbers. In general, we can solve those kind of expressions. Some of them are easier than others. Let's see what this one looks like. Let's go ahead and write it out like this. Right? I now have that x squared over 0.020 minus x squared, quantity squared, is 0.58. Can we solve that one? Yeah, that one actually solves pretty easily, because we can actually just take the square root of both sides. If we take the square root of both sides, we get x over 0.0200 minus x is plus or minus, what do I get if I take the square root of 0.58? You get 0.76. Remember, you always get that plus or minus when you take the square root, because right, if I take 0.76 squared, I get 0.58. If I take minus 0.76 squared, I get 0.58. So we've got two roots here that we're going to have to figure out. So what are we going to do? Well, let's go ahead and rearrange and solve for x. So let's use our positive root first. We're going to say x over 0.0200 minus x is equal to positive 0.76. We multiply both sides by 0.0200 minus x. That cancels out over here, and we get x equals 0.76 times 0.02 minus 0.76x. Right, add 0.76x to both sides, and you get 1.76x is equal to 0.76 times 0.0200. Right, just algebra at this point. If you solve that out, right, that little x there isn't our variable x, so I'm going to go ahead and change that to times. Okay, if you solve that, you get that x equals 0.0086. Now, you also have to solve for the negative root. I'm going to let you do that one and tell you that for the negative root, you get x equals minus 0.063. This is our minus 0.76 root. Right? We have to consider both of those and figure out if there's a way of eliminating one as a possible answer. And there is in this case, because we know from our table way up here that at equilibrium we should have a concentration of x of CO2. And if we have x CO2, x better darn well be positive, because negative concentrations are not possible. Therefore, we can actually eliminate this second root because it doesn't make sense. Right? It's a negative concentration. We can't have a negative concentration in equilibrium. So we know our root is 0.086, which means the concentration of CO2 and the concentration of H2 were both equal to x, and so those are both going to be 0.0086 molar. Why? Because I'm now talking about concentrations. I have to take that reference and put it back out. The thing to remember is when you're just talking about the concentrations, put that molar back. Okay. What about my concentrations of CO and my concentration of H2O? Right. They were 0.0200 minus x, and if you plug that in, you get 0.0114 molar as my concentration of those ones. Whew. You can actually check your work too by plugging those numbers back in to your equilibrium expression and make sure that you get a k value of 0.58. It's a great way to check your own work, especially on quizzes and exams. I'm not going to do it here, but you certainly can. So that was kind of a long problem, right? We had to do a bunch of different steps, write out that table of things that changed, and then find our k expression. Let me scroll up here. Right? We had to write out the reaction, figure out what we started with and what changed. This little thing of writing out initial, change, and equilibrium, people have a name for them. They're called ICE tables. And so we're going to use ICE tables all the time, initial, change, equilibrium, in order to set up these kind of problems. Once you write out your ICE table, you write out the equilibrium expression. You substitute in that equilibrium line into your equilibrium expression, and then you solve. And part of what we're going to do in this class is figure out a bunch of different ways of solving for these in different scenarios. Okay, this was one way where we had this nice square form, so we were just able to take the square root of both sides, but life isn't always that kind to us, so we're going to find other ones as well. You got to find when there's multiple roots, you got to find both roots and usually eliminate one for being unreasonable. Another reason to be unreasonable is, let's say our second root was 7. That means our final concentrations of our CO and H2O would have been 0.02 minus 7, or a negative number. That just wouldn't make sense. So that is one example. Let's go ahead and do a second example. Right? So here we've got H2 and I2 forming 2HI. We've got a K value of 49.7 at 458 degrees Celsius. We're going to start with 1 molar H2 and 2 molar I2. So you can already see that we're probably not going to get that square thing in there to help us along. So we're going to find our equilibrium concentrations. What's the first thing we do? ICE table. Second thing, K expression. Third thing, we're going to sub the equilibrium line from the ICE table into K. And the fourth thing we're going to do is solve. Okay, so the first thing we're going to do is write our ICE table. We've got H2 plus I2 goes to 2HI. And you'll notice when I do my ICE tables, I'm not being careful about writing my phases and things like that. It's not really important to do, although you should pay attention if there's any solids or liquids, so we don't include those in our K expressions. Right? So ICE, I, C, and E. We look back up, our problem statement tells us H2 is 1 molar, I2 is 2 molar, 1.00 molar, 2.00 molar, no HI. How do we know it's no HI? Because nobody told us there was. So in the problem statement, it didn't say anywhere, I've got HI, I don't have HI. If it's not mentioned, you can assume that there's none of it. Okay. So we have none of that. What do we know? We're going to make some HI as we go along. So I'm going to do this in not the best way first, and then I'm going to show you kind of a better way to do it. You're like, well, I'm going to make how much HI? I don't know. Let me call it X. Now we've got this stoichiometry problem. If I made XHI, how much I2 did I make? And it can get a little bit confusing because you're like, well, did I make twice as, no, I used up twice as, no, half, no. Okay, so if I'm using it and I'm producing the 2, that means I used 1. So if I have X, is that 2? It can get really, really confusing. There's 2 ways around the confusing. One is to just do the stoichiometry, right? I've got X molar HI, and you do the stoichiometry that there's 1 mole, let me just call it moles just for, 1 mole, I don't know why I did that, of I2 for every 2 moles of HI, right? That's just stoichiometry from our balanced chemical equations, and we'd get X over 2 moles of HI. And in constant volume situations, moles and molarity are essentially the same thing. And so I'd go X over 2 here and X over 2 here, and then move along and add those up. Totally doable. You can absolutely do it that way. There's nothing wrong with doing it that way. However, it gets a little bit tedious when you have a lot of stoichiometry. You've got 3s here and 7s here and 5s here. It can make it really, really hard to figure that out. So it turns out the easiest way is to make your base number X. And then the stoichiometry actually all does it by itself if you just put your coefficients in front. So I'm going to say my base number is x, but I'm going to put a 2 in here that I get from the stoichiometry there. I know I'm using up, so I still have to put the negative there. That's still on me. But I'm going to put a 1 in front of it from the stoichiometry there, and an x here. I'm going to put a 1 in front of it from the stoichiometry here. No matter what numbers appear there, if there was a 7 in front of that I2, then I'd have minus 7x. If there was a 4 in front of that H2, I'd have minus 4x. That way is a little bit easier. I'm always going to use this way moving forward, where kind of my base is x, and then I just put that stoichiometric coefficient in front for each of my things, just because I find that by far the easiest way to do it rather than having to deal with fractions. So what do? I add up I plus c to get e, 1.00 minus x, 2.00 minus x, and 2x. You'll notice I stop including units here, okay? Because as soon as we start putting these into our equilibrium expressions, we divide by reference concentration, so we don't have units. Breathe. So we can stop including units. I always include them in the first step as a good matter of habit to make sure I have the right units, because sometimes we don't have the right units, or we have mixed units and it doesn't work out so well. Next, I write my K expression. It's going to be the concentration of HI. This computer sometimes. The concentration of HI squared over the concentration of H2 times the concentration of I2. And my K value for that was 49.7. I substitute in my equilibrium line. It's 2x squared. Very important. Very, very important that you don't write 2x squared. Your concentration was 2x. Your concentration was not x. You're not taking your concentration and multiplying it by 2, right, in this step here. You're taking your concentration and squaring it. So you've got to make sure that your entire thing, everything in this line, goes inside that parentheses. So you get the quantity 2x squared, not 2 times x squared. Very, very important. We're going to see that many times as we go through different examples. Here, 1.00 minus x, and here 2.00 minus x. And that's going to be equal to 49.7. All right. So how do we solve that one? Well, we don't have the same thing we had before, which is the ability to just take the square root of both sides, because we don't have a perfect square on the bottom. So by golly, the best way to do this one is just going to be to write it all out. We're going to get 4x squared over here. Let's go ahead and take everything off to the right-hand side. So I'm going to multiply both sides by the denominator. I get 49.7 times 1.00 minus x times 2.00 minus x. And so now I can just work on that part. And I've got 49.7 times 2.00 minus 3.00x plus x squared, right? FOIL, first, outer, inner, last. And so I get that. Boy, if I have to multiply 49.7 through all of that, it's a little tedious. So what I'm actually going to do is just divide both sides by 49.7 to get that out of here, because then I just get a number over here. And 4 over 49.7 is going to be 0.0805 x squared, and that's going to be 2.00 minus 3.00x plus x squared. Lots of algebra, lots and lots of algebra. Hope you liked your algebra class. All right, remember, for solving squares, we're going to use the quadratic formula. And for the quadratic formula, you need to rearrange everything so that it's equal to 0. So I'm going to go ahead and do that. I'm not going to show every little step. I get 0.920x squared minus 3.00x plus 2.00 is equal to 0. If you don't get something like that, you can come find me and we can talk about it and figure that out together. And then what is the quadratic equation? You get that x equals the square root, minus b plus or minus the square root of b squared minus 4ac over 2a. How exciting! And you're like, Professor Clements, do you know I can just plug that in Google and it'll give me the answer right away? Yeah, I know that. I totally know that. In fact, if I were solving this problem on my own, I'd plug it into Google and I would solve it that way. But I want us to practice some of these other methods. You think, why? Why would you practice these other methods? Because it turns out that some of the things that we're going to be doing, not this one as much, I got to admit, plugging into the quadratic equation, not something you're probably ever going to be doing much in your life. But some of the other ways that we're going to be solving things are really important for learning how to solve even harder problems that you can't plug into Google. So part of it is the practice of how do we solve really hard problems, not how do we solve this specific problem that Google can totally solve for us. All right, so let's go ahead and keep moving forward. Let's go ahead. We've got to figure out minus b, so that's going to be a positive 3.00 plus or minus the square root of 3.00 squared minus 4 times AC, which is going to be 0.920 times 2.00 over 2 times 0.920. Plug, chug, calculator. And what do you get? You get that it is 1.63 plus or minus 0.70, which is 2.33 or 0.93. Now, like I said, one of the first things you want to do when you get your two different roots for x is you want to check to see if one of them is unreasonable. Let's go back up to our equilibrium line here. Our equilibrium line tells us that our equilibrium concentration of H2 is going to be 1 minus x. So let's go ahead and look down here. If I take 1 minus 2.33, I'm going to get a negative value. So just from not being reasonable, I can eliminate that root. And so I know that my x is actually just going to be 0.93. And so all you do to find your problem, your answers now, is you just substitute that x into all the different things you had in your equilibrium line in your ICE table. And so we got that the concentration of HI was 2x, or 2 times 0.93, or 1.86 molar. We've got that the concentration of H2 was 1.00 minus x, or 1.00 minus 0.93, or 0.07 molar. These are our answers. And the concentration of I2 was 2.00 minus x, or 2.00 minus 0.93, or 1.07 molar. And so now we've got equilibrium concentrations for all of our species. It's a little tedious, absolutely it's a little tedious, but if you run across a problem like this on a test or quiz, I do want you to go forward and do the quadratic equation and all that kind of stuff. What we're going to find, so just so you know, you're like, oh, I can't believe I'm going to have to do that so many times. No. What we're going to find is that there's ways we can avoid using the quadratic equation that make our lives a lot easier, assumptions we can make, and we're going to see those in our next set of videos. All right, if you plug all that back in, hopefully you should find a k value that's pretty darn close to the k value you started with. It's not going to be exact because we have some low sig figs in some of our numbers here, but it should be awfully close. All right. Your turn to try this. We've got a reaction N2O and H2O goes to N2 and H2O. K is 1.7 times 10 to the minus 4th at a certain temperature. The following concentration is introduced into a chamber. Which direction will the reaction proceed? So how do we figure out which direction a reaction will proceed? Go. Hopefully you came up with Q. Right? And Q is just a way of saying, how do I know which direction this goes? And this is going to be our products over our reactants. You plug in those values that we got there, and you should get that Q is 4.2 times 10 to the minus 4th. Right? So that is Q is greater than K. It's slightly greater than K. It's not hugely greater than K, but what does that mean? Right? The reaction has to get smaller over time. This has to get smaller. This has to get bigger in order for Q to become K, which is its ultimate goal. Q will always become K given enough time to obtain equilibrium. So this reaction will go to the left. All right. Here's another one. We're going to start with 0.5 moles each of NO and Cl and no NOCl. And after 150 seconds, 0.25 moles of NOCl has been produced, and how much Cl2 is left? So your turn for that one. Like Professor Clements, this doesn't really have anything to do with what we just did. It does, because it's the stoichiometry part of it, which for a lot of people, it's a hang-up of getting this ice table stuff down, is getting the stoichiometry part right. So I'm helping you work on the stoichiometry part. Right? Let's do it as an ice table. So we're going to do NO. We're going to do Cl2, and it goes to 2NOCl. We're going to go ahead and do an ice table just for practice. So we start with 0.500 moles, 0.500 moles, and none of that. We know as it reacts, we're going to use that x as a base with our coefficients in front. We know we're using up the stuff here, right, because the reaction can only go to the right because there's no products to react. And so we add those up, 0.500 minus 2x, 0.500 minus x, and 2x. So since we know that the concentration of NOCl is 0.250 moles of NOCl is 0.250 moles, that's equal to 2x, which means my x is equal to 0.125 moles. That's very confusing for a lot of people because they want that moles of NOCl to be equal to x. But it's not. I mean, that's not what we said. We just defined it because we can as 2x. Right? We could have defined that as x, but then we would have had x's over 2's and stuff in our other thing. We would come up with the same answer. So that's very hard. People always want that to be equal to x, but it's not. It's 2x by definition because we defined it that way. And so I get x is 0.125 moles. What am I trying to find? I'm trying to find out how much Cl2 is left. Cl2 was 0.500 minus x, or 0.500 minus 0.125, which should get me 0.375 moles. All right. That was it for our first introductions to using the equilibrium constant to find values at equilibrium. And we did one, which was a pure substitute method, and we did another that was we actually had to go in and find the quadratic equation and solve it. And we did a third one that was we were able to get a square that we square rooted. But in all of these, there's a lot of algebra involved, a lot of steps to make mistakes on. So you just have to be diligent in your work. And that's why we write this stuff out step by step and make sure we're following it well. Because it's really easy to forget a square, to forget this. So that's what we got to do. Thanks, and hope this was useful. Bye.